Okay, we're now going to move on to a subject which superficially seems to have very little connection with computer science. But in fact, as I hope I'll be able to demonstrate, this topic actually occurs in a number of quite advanced areas of computer science and is in fact extremely important within computer science. So this is the subject of what are called complex numbers. So in the first few lectures, I'm going to be talking about properties of complex numbers, and I'm then going to concentrate on applications in computer science where complex numbers arise. And as is usual, I'm going to start off with a pretentious quote. And this perhaps summarizes a number of feelings about complex numbers. Gott weiß, wie das geschah. God knows how that came about. It's a quote from Richard Wagner's Meistersinger von Nuremberg. So, how did that come about? Let's go right back to the start of the module in one of the topics we looked at there. The notion of what I'm going to be calling a complex number. This comes about in the problem of considering roots of polynomials. So we claimed that every single polynomial of degree k has k roots. Okay, well if that's true, what are the two roots of this polynomial? This is degree 2, it should have two roots. What are they? Well, the mechanism, the way we deal with that problem, that leads to what will be the final class of numbers that we consider on this module, the so-called complex numbers. Okay, so let's go back to our two roots problem. The two roots of this polynomial, x squared plus 1. First of all, those two roots cannot be real numbers. Why is that? If we take any real number and square it, the outcome is non-negative. If we add 1 to a non-negative number, we get a positive number. What we do not get is the outcome 0. So the roots cannot be real numbers. Well, let's imagine a class of numbers which these roots could belong to. And since we've imagined that class of number, let's call those two roots I and minus I. So what do I mean by that? What I mean is that this object I will have the property that when we square it, we get the outcome minus 1. When we take the object minus I and square it, then we get the object minus 1. And so these objects, I minus I, those are the roots of this degree 2 polynomial. And to see that, we can just go through the computation. We take I in place of x, we square it, we add 1, we get by definition minus 1 plus 1, which is 0. And we do the same thing with minus I, we get the same outcome. So these objects, these solve this what are the two roots of x squared plus 1 problem. The answer to that question is those roots are I and minus I. What about other cases? What about the example I mentioned when I was talking about polynomials, x squared plus 9? The two roots we have for that polynomial, 3 times I and minus 3 times I. And why is that? Because if we put 3i as our value of x, then we get 3i squared plus 9, which is minus 9 plus 9, which is 0. Similarly with minus 3i. In general, if we take any degree k polynomial whose coefficients are real numbers, then every single one of the roots of that polynomial can be written in the form some real constant a plus this object I multiplied by some real constant b. Now the way we refer to this part, we call that the real part of z, and we use this notation. The way we refer to this object, the object we multiply I by, this is called the imaginary part of z, and we use this notation. Now, this collection of objects, a plus I times b, where a and b are both real numbers, these form the set of what we're going to call the complex numbers. So, just to recap, a complex number takes the form some real number a plus this object I multiplied by some real number b. So we have in a complex number a real part and an imaginary part. Those pairs, real part, imaginary part, they form a structure which I'll be referring to as the complex plane. And the complex plane we can think of as our standard two-dimensional axis. But all we do is we replace the horizontal axis with the real part, and we replace the vertical axis with the imaginary part. So what are the kind of basic operations we're interested in performing on complex numbers? So suppose we're given two arbitrary complex numbers, u and v. We might want to look at addition of those numbers. How do we add two complex numbers? Well, we just add the corresponding components. So the real part for the addition of our number, we just add the corresponding real parts of our complex numbers. For the imaginary part, we just do the same thing. The imaginary part of our added complex number, we just add the corresponding imaginary parts of the contributing complex numbers. We have this new operation, what is called complex conjugate. And for that operation, well, we don't touch the real part, so the real part of the complex conjugate is exactly the same as the real part of the original number. For the imaginary part, what we do is we change the sign. So the imaginary part of the complex conjugate is just the negative of the imaginary part of the input value. One consequence of that definition is if we take the complex conjugate of the complex conjugate of our number, then all we get is the original number back again. We have this notion of modulus, or size of a complex number. And the way that's defined is we take the real part of our complex number and we square it. We take the imaginary part of our complex number and we square it. We add the two quantities and we take the positive square root of the outcome. So here are some examples. Suppose our two complex numbers are 3 plus 4 times I and 1 minus 2 times I. For addition, we add the real parts and we get the outcome 4, 3 plus 1. For the imaginary part, we add the two imaginary parts, we get 4 plus minus 2, and we get the outcome 2. For complex conjugate, if our complex number we are starting with is 4 plus 2i, the complex conjugate, the real part doesn't change, it remains as 4. The imaginary part, we negate the sign. So the imaginary part, we get minus 2. So our complex conjugate operation, for this complex number, this is the outcome. For size, if we are looking at this complex number, we take the square root of 3 squared, we add to that 4 squared, and we get the outcome, the square root of 25, which of course is 5. What about more involved operations? So we saw with the case of vectors and with polynomials, this operation which I referred to as scalar multiplication. So we take a real constant value and we multiply some complex number by that real constant value. Well, it's exactly the same process as we had with scalar multiplication with two vectors. We multiply the real part of our complex number by the constant, and we multiply the imaginary part of our complex number by that constant value. We now get a much more involved operation, an operation where we start to use the definition of this object I. So we want to multiply two complex numbers. Well, if we look at the algebraic definition, that corresponds to this process here. We are multiplying this object by this object here. So if we expand that, what we get is this form here. We have the real part of u multiplied by the real part of v, this term. We have the imaginary part of u multiplied by the imaginary part of v, the whole thing multiplied by I multiplied by I. And we add on to that the real part of u multiplied by I multiplied by the imaginary part of v, this term, plus the imaginary part of u multiplied by I multiplied by the real part of v, this term here. We factored out the I in deriving that term, and now if we simplify that expression, what we get, the real part is the real part of u multiplied by the real part of v, this term, minus the imaginary part of u multiplied by the imaginary part of v. And the reason why this minus sign appears is we have this contribution I squared. And I squared is the object we have defined to have the outcome minus 1. For the remainder, the imaginary part is just this term here. Okay? So that's complex multiplication. Let's look at the example of complex multiplication. Well, the scalar multiplication operation is very straightforward. For complex multiplication, what if we are multiplying this object by this object? What happens? Here's the algebraic form of that multiplication. If we expand it, we have 3 multiplied by 1 plus I multiplied by I multiplied by 4 multiplied by minus 2. And we're adding on to that I multiplied by 3 times minus 2 plus 4 multiplied by 1. Now if we simplify that, then what we get for the real part of our complex number is 11. What we get for an imaginary part is minus 2. So overall, the outcome of our multiplication is a complex number, 11 minus 2 times I. Complex division becomes much more involved yet. So suppose we want to divide a given complex number by another complex number. Well, we know already, we saw in the previous slide, we know how to multiply two complex numbers. So the only thing we need to consider in defining division of two complex numbers is how to define the result of dividing one by a complex number. Well, first of all, exactly as with normal division, we have a precondition. Division of complex numbers is not defined when the denominator is equal to 0. So we have the precondition that this complex number cannot be 0. And the way in which division 1 over a complex number is defined, it's just we take the complex conjugate and we divide that by the size of the complex number squared. Now that may look a bit odd. To check it's correct, we just multiply this structure by the complex number we are using. And what we get, V multiplied by the complex conjugate of V, it's easy enough to check that is this. This length, the size of a complex number squared, is just this term here. These two are equal, and so we get the outcome 1. So here's an example of complex division. If we're forming the complex number 1 divided by 3 plus 4 times I, we form the complex conjugate. That's 3 minus 4 times I. We look at the length of this complex number squared. We've seen that that's 25. So the outcome, 1 divided by u, that's the complex number 3 minus 4 times I divided by 25. So let me just summarize what we've seen and what we're going to move on to look at. First of all, there are many different ways of describing complex numbers. Some of those we're going to see in the next lecture. So these are structures such as the matrix form, Argand diagrams, polar coordinates, the Euler form of the complex numbers. As I said, we're going to look at those next. We're also going to quite briefly look at how calculus has to be extended in order for it to apply to complex numbers. In the second part, once we've finished looking at the technical material for complex numbers, so these are these two sections, I'm going to look at what is really of interest, how we use complex number theory in computer science. And so these are going to be topics such as an object called quaternions and advanced graphics. It's a structure called the Fourier transform and how it's used in developing fast arithmetic algorithms. I'm going to briefly look at algorithm analysis and how it uses complex integration. I'm going to talk also about complex number sequences and how these are used as a method of composing music.